Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to present a topic, the Compton Effect in Physics, BTech first semester engineering. So, I would like to start with Compton Effect. Summary so far related to the photons. Einstein postulated the existence of particles called photons to explain the speed of light, explain instantaneous emission of electrons in photoelectric effect, frequency dependence, further confirmation of the photon picture provided by the Compton effect, 1922-23. Einstein postulated this EP equals to HF equals to hc by lambda. Einstein's special theory of relativity, 1905. The laws of physics are the same in every inertial frame of reference in which Newton's first law is valid. The speed of light in a vacuum is same in all internal frames of reference and is independent of the motion of the source. The velocity of light cannot be exceeded. Many important consequences: length contraction, time dilation, effects at high speed, mass energy equivalence. Now this is the little bit about relativity. Some graphs. Momentum, kinetic energy at high speeds. Now the energy and momentum relationship E equals to mc square upon Einstein theory of relativity, that is given by E equals to mc square upon root 1 minus v square upon c square. Energy of the stationary particles by mc square, P equals to mv upon root 1 minus v square by q. So relativistic expression for energy and momentum. So E square is equals to mc square whole square plus pc whole square. E square is equals to mc square whole square plus pc square. Consequently, particle with zero rest mass, example photon, has momentum p, given by E equals to E by c, hf or h nu by c equals to h by lambda. Now the Compton effect, X-ray source, target, detector. X-ray scattered from target containing very loosely bound electrons. Wavelength of the scattered X-ray found to be different from that of incident X-rays and to depend on detection angle phi. Lambda dash minus lambda is equals to h upon MEC 1 minus cos phi. The Compton effect, the intensity distribution of the radiation scattered by free electrons with the different scattering angles. Treat Compton scattering as a two-particle collision between photon and initially stationary electron, obeying conservation laws for energy and momentum. Before energy, photon, electron. After this, the conservation of momentum or the conservation laws of energy and momentum takes place. Vector triangle, consider magnitudes of vectors pi, pf and pe. Pe square equals to pf square plus pi square minus 2 pf pi cos phi. We are dealing with velocities at or close to speed of light, so need to use relativistic expressions. Initial energy, final energy. PIC plus MEC square is FC plus EE. EE is equals to PIC minus PFC plus MEC square. E square is equals to this final results or the relation come out. General expression. Divide both sides by c square we carefully. We get this. After that we get this. Now Compton scattering, conservation of energy and momentum. Energy, this is the expression for the energy. This is the expression for the momentum. Finally, we just get this result, minus 2 pi pf cos phi minus 1 pi pf minus me cos equals this. This is the final result. The observed experimental result is lambda dash minus lambda is equals to h by mc 1 minus cos phi. Is entirely explained by the photon electron scattering model, further proof of the validity of the photon concept. The maximum wavelength shift for phi equals to 180 degree, del y equals to 2h by mc. H by mc is known as the Compton wavelength of the electron. Very small work it out, so Compton effect only observed for short wavelength radiation, X-rays, gamma rays. So we have seen that light can be described as a stream of particles called photons, but we don't have to take this picture too literally. Instead, you can think of the situation as electromagnetic wave. Electromagnetic wave exchanging energy and momentum which change particle in quantized amount. Of formation of bright and dark fringes are obtained by the Young's double slit experiment, which I had already shown in the previous slides. So the formation of interference fringes is explained on the basis of wave theory of light. According to it, the light propagates in the form of wave fronts. If you remember, I had already discussed this. The interference of fringes explained on the basis of wave theory of light. According to it, light propagates in the form of wave fronts, and each point of this wavefront acts as a source of secondary wavelet. When a wavelet emitted from the light source is incident on the slit S1 or S2, two slits are there. The secondary wavelets are emitted by the parts of the wavefront exposed by the slits. These wavelets superimpose each other in space between the slits and the screen. At the point of on the screen where the crest of one wave coincide with the crest of another wave, or trough of one wave coincide with the trough of another wave, waves are superimposed in the same phase. At these points, the resultant amplitude is maximum. So the intensity of the intensity of light is maximum. Hence, bright interference fringes are formed there. When a crest of one wave coincides with the trough of another wave, or vice versa, waves are superimposed in opposite phase. At these points, the resultant amplitude as well as intensities are minimum, or we can say it is zero also. So hence dark fringes are formed there, since secondary wavelets are emitted from the same wavefront, hence their amplitude will be same. Therefore, the resultant amplitude or intensity will be zero in case of distractive interference. So Huygens principle, every point on a wavefront acts as the point source. The wavefront as it develops is tangent to the their envelope. So this is the primary source as is showing to you, and the A to B line is showing the wavelets or wavefront, that is another source of secondary source of light generate from the primary source, and the light propagates in the form of wavefronts, and again the line CD generates a new wavefront, and so on and so on. Wave versus particles, that is Huygens principle and diffraction. We will later discuss this, and before discussion to this, I'll let you know the law of or principle of superposition, because in the wave theory, the superposition principle of light takes place. When two or more waves superpose or superimpose in a certain region, the resultant displacement, electric, just wait a minute. Yes. The certain reason, the resultant displacement, electric or magnetic field vector in case of light is the vector sum. Of displacement caused by different waves individually. This is called superposition principle. If E1, E2, E3 are the disturbance produced by the individual waves, then the resultant disturbance will be the vector sum of all the individual disturbance. If the disturbance of all the waves are in the same direction, then the resultant displacement or disturbance will be the algebraic sum of the displacement of all individual waves. For this, we are just going to perform one experiment. Let us take two waves of same frequency omega, but different amplitudes are emitted from a coherent source S1 and S2. These waves traveled uh, distance x1 and x2 respectively in the nearly same direction, and that is almost we just consider to be in the x direction. Therefore, meeting a certain point and with the initial phase of phi 1 and phi 2 respectively. The equation of the disturbance produced by these waves at any time can be called as or given as E1 is equals to E naught 1 sine omega t minus kx1 plus phi 1. And after that, this equation can be rewritten as the second equation is also taken to be considered. E2 is equals to E naught 2 sine omega t minus kx2 plus phi 2. Uh, Now we just assume that, kx1 minus phi 1 is equals to alpha 1 and kx2 minus phi 2 is equals to alpha 2. The equation of waves can be written as E1 equals to E naught 1 sine omega t minus alpha 1 and E2 equals to E naught 2 sine omega t minus alpha 2, where omega is equals to 2 pi nu or 2 pi nu, or nu is the frequency of the wave, where k is equals to 2 pi by lambda, and lambda is the wavelength of the wave. From the superposition principle, the resultant disturbance can be added up algebraically. E is equals to E1 plus E2, and by substituting the values of E1 and E2 by the use of superposition principle, finally we get some equation, and it is come out to be E equals to A sine omega t cos theta minus A cos omega t sine theta, and which is also can be written as E equals to A sine omega t minus theta. This equation represents the resultant wave produced by the superposition of two waves. Its amplitude is A and phase angle is theta. Squaring and adding both the equations, almost we get an amplitude, and it is come out to be k delta minus phi k delta minus 5. Yes. So this is the principle of superposition. Now I'll let you know some. Just wait a minute. So the Huygens principle and the law of refraction. Just wait a minute. There's some disturbance in the. Sorry for the disturbance. Yes, Huygens principle, the law of refraction. Huygens principle can also explain the law of refraction. As the wavelet propagates from each point, they propagate more slowly in the medium of higher index of refraction. This leads to a band in the wavefront and therefore in the ray. Now, I just want to give some brief introduction about the incoherent and coherent sources which are to be used for producing the interference. So, because I am using the word, what do you mean by the coherent source? And coherent source are to be taken, and by using the Young's double slit experiment, we had already checked out this coherent source produce the wavefronts, and these wavefronts generate the secondary wave. Emission of light, radiation from each light source is the transition of a very large number of atoms from the excited state to the ground state. After receiving energy, atoms remains in the excited state for about 10 to the power minus 8 seconds and then return back to the ground state. No correlation of phase is found in the radiation emitted from these atoms because the process of emission of radiation from the atoms is random. If we take two independent light sources, the phase difference between the waves emitted by these sources will not remain constant in time but will vary at random. Thus, the light sources are said to be incoherent if there is no definite phase relation between the waves emitted by the sources. That is, the phase difference between the waves vary with time, are known as incoherent source of. Emitted by the incoherent source will not be stable because sometimes these waves will satisfy the condition of constructive interference. Uh, so the interference pattern obtained from the waves emitted by the incoherent sources will not be stable because sometimes these waves will uh, satisfy the condition of constructive interference, and other times they will satisfy the condition of destructive interference. The change of intensity in interference pattern will be so rapid that one cannot see the interference. When the phase difference between the between the waves received at any place from a light two light source does not change with time, that is, it remains constant, then these sources are called coherent sources. In that case, the interference pattern will be stable and one can see the interference. In actual practice, it is not possible to have two independent sources which are coherent. If we construct two sources from one light source by any means, then whatever change occurs in the phase of the wave produced at any instant from one source, the same change will occur in the phase of the wave produced at the same instant from the another source. In this way, the phase difference between the waves produced by the both source remains constant. Thus, from the superposition of waves produced by two coherent sources, a stable interference pattern can be obtained. There are two types of coherence. One is the temporal coherence and the coherence in time, and the second is the spatial coherence, that is coherence in the space. So, if I'm just give you the brief introduction about the temporal coherence, when a light waves of fixed frequency are emitted from a light source, it is said to be monochromatic source, which we had already discussed. What do you mean by the monochromatic source? Such type of light wave can be represented by an infinitely long sinusoidal wave and its frequency spectrum I had already discussed in the previous slides. Practically, light waves are emitted from the source when the electrons in the higher excited state transit to the lower or ground state. The duration of this transition is about 10 to the power minus 9 seconds. The sine wave character of the emitted wave does not extend to infinite time, but only for this limited time. So, next. So the Huygens principle can also explain the law of refraction. As the wavelets propagate from each point, they propagate more slowly in the medium of higher index of refraction. This leads to the band in the wavefront and therefore in the ray. So Huygens, the frequency of the light does not change, but the wavelength does as it travels into a new medium, and we just get the relationships through the help of Snell's law. Huygens principle. So highway mirages are due to the gradually changing index of the refraction in heated air. So this is the phenomena how the mirage appears to be seen on the highways in the sunny hot days. So this is the Young's double slit experiment which we had discussed. Just have a look for this. We just take a cardboard in which we had just make two slits, S1 and S2, and the monochromatic source of light is, that is sun rays, are be just incident on that cardboard, and the viewing screen particle theory prediction, viewing screen actual. So what we are just observe and what we are just get. So that fringes obtained actual are known as the fringes, interference of the light in a constructive and destructive manner. So, just wait a minute. So the condition for sustained interference, there are certain conditions for sustained interference which are very important. The condition for sustained interference are the wavelength or frequency of the interference wave produced by the light source must be same. They are very same, the wavelength or the frequency of the interfering light. The light sources must be coherent. That is, the phase difference of the wave emitted by them must be constant with respect to time. The interference or interfering waves produced by both the sources should propagate almost in the same direction. The amplitude of the wave should be nearly equal so that the fringes may appear clear and distinct. If there should be good contrast between the fringes. If interfering waves are polarized, then polarization state of both waves should be same. The path difference between the waves should not be very large compared to the wavelength. The path difference should not be very large compared to the wavelength of the light. So, and we are just know that practically coherent sources are not possible, but we are need to produce the coherent sources. So there are two methods of producing the coherent sources. First is by the division of the wavefront, or second is by the division of the amplitude. So the interference of light, coherent sources are produced by first, that is division of wavefront. In this method, the incident wavefront is divided into two parts, and these divided wavefronts, after traveling or after traveling different optical paths, are made to superimpose at very small angle. This produces interference fringes. These two parts of the wavefront are equivalent to the wavefront produced by the two virtual coherent sources. For this method, it is required that the light source should be narrow or a point source. This method is used in Young's double slit experiment and Fresnel's biprism experiment. Second method for producing the coherent source is the division of amplitude. In this method, the amplitude of the incident wave is divided into two or more parts by partial reflection or refraction, and these divided parts are made to superimpose by spatial arrangement. This produces interference fringes. For this method, it is required that the source should be a broad source. Interference fringes are produced in thin films. Newton's ring experiment and Michelson interferometer by this method. So, next, the interference occurs because each point on the screen is not same distance from both the slits. Depending on the path length difference, the wave can interfere constructively bright or destructively dark spots. So this is the physics or the equation related to the interference pattern, constructive interference and destructive interference, depending upon their phase and the frequency. Between the maximum and the minima, the amplitudes vary smoothly. Since the position of maxima except the central one depends on the wavelength, the first and the higher order fringes can have a spectrum of colors. So Fresnel biprism is an experiment in which two coherent sources are obtained by refraction from Fresnel biprism. It consists of two small prisms placed base to base, placed base to base. Their refractive angles are equal and very small, of order of 1/2 degree. Or in fact, biprism is made out of a single piece of glass by grinding and polishing. By grinding and polishing. So, in order to obtain interference fringes, a vertical narrow slit S is illuminated with a monochromatic light produced by a sodium lamp. Biprism is placed in front of the slit as in such a way that the middle edge of the biprism remains parallel to the slit. The slit is perpendicular to the paper in the previous figures. When a cylindrical wavefront emitted by the source as is incident on the refractive surfaces AB and BC, half of the wavefront is reflected by AB and rest half of the wavefront is reflected by BC. The refracted rays appear coming from S1 and S2, that is slits. In this way, the two virtual images are formed. In the overlapping region of the light diverging from the slits, interference fringes are formed. As a result, interference fringes of equal widths are observed in this region. These fringes can be seen with the help of eyepiece. So, this is almost where we had covered everything related to the interference Now, there are some more definition which we need to discuss about or for the interference fringes produced by the white light. A white light has several colors whose wavelengths vary from 4,000 angstrom to 7,000 angstrom. When the slit of biprism is illuminated with white light, two coherent virtual sources S1 and S2 are produced after refraction from the biprism. Interference patterns are formed on the screen for all wavelengths. The fringe widths are different for different colors. Thus, the interference pattern on the screen will have the following characteristics. Uh, Central fringe, fringe of zero order of interference pattern is always white, which is shown in the figure. Which is shown in the figure. All the waves of different colors coming from slits reach the center with the same phase. Thus, the bright fringes due to all colors will overlap at the center and will produce the fringe of white color. Outer edge of dark fringe is found violet and inner edge is found red. Smaller number of colored fringes are seen. A uniform illumination is observed at the place of fringes of high order because there is overlapping of waves of different colors in that region. Fringe width is non-uniform. Now, there is a determination of thickness, that is refractive index of thin transparent film by biprism. So, when a thin transparent film or thickness d of the refractive index mu is placed in the path of secondary wavelets coming either from the sources S1 and S2. So, this is some mathematical relation will take place for calculating the thickness and all that. I'll show in the next slide. Wait a minute. So this is I had already discussed with you the visible spectrum. The index of refraction of material varies somewhat with the wavelength of light. Now we are going to start with interference in thin films. No. If the interference in thin films, when the light is incident on the thin films, such as oil layer or on water, then the thin mica sheet or a soap bubble, light is uh, reflected and refracted from the upper and lower surfaces of film. These light rays, when made to interact each other, produce interference pattern. Light of different wavelengths produces different interference fringes. The dispersion of white light from this thin transparent film is due to the interference phenomena. And there are some important points like complementary interference is one word over there. So, complementary, the condition of maximum minima is reflected light source are just reverse of those in transmitted light. Hence, if the upper surface of the film appears bright in monochromatic reflected light, then the lower source surface of film will then appear dark in transmitted light and vice versa. Thus, one can say that interference in reflected light is complementary to interference in transmitted light. So, interference in ultra thin transparent film, when the monochromatic light is incident on ultra thin transparent film, That is, the time is very, very less than the wavelength, then the change in the phase is equals to zero. In this case, it will satisfy the condition of destructive interference, and hence the film will appear dark in the reflected light. But in transmitted light, the film will appear bright, as above conditions satisfy the condition of constructive interference. So transparent film in white light, when the white light is incident on the transparent film, some wavelengths of white light may satisfy the condition of destructive interference, and hence these wavelengths of colors will be missing and other wavelengths will be present. The colors which are present depend upon the thickness of the film and the angle of incidence, and form their own interference pattern. Thus, we see colors in thin film. Now, the types of fringes exhibited in thin film. Generally, there are two types of fringes appeared in the thin film. Uh, Fringes of equal inclination and fringes of equal thickness. So when a monochromatic light of wavelength lambda is incident on a transparent film of constant thickness, the fringes are the locus of all points where the angle of incidence is same. Such fringes are called fringes originating from the same inclination on the film. Such type of fringes are observed in Michelson interferometer. And fringes of equal thickness, when a monochromatic light of wavelength lambda is incident on a transparent film of varying thickness, that is non-uniform thickness, the fringes are the locus of all the points where the thickness of the film is same. Such fringes are called Fizeau fringes or fringes of equal thickness. Next. Just wait a minute. Now, the diffraction by a single slit or a disk. The light will also diffract around a single slit or obstacle. So, if you place an obstacle in front of sound source, sound is always heard behind the obstacle. It is possible only when the sound waves bend around the corners of the obstacle and reach the listener. The phenomenon of bending of the sound wave surrounding the corners of the obstacle is called diffraction of sound. So, similarly, the outer boundary of the shadow of an obstacle formed by light is not sharp but blurred because some part of the light bends around the corners of the end and enters into the geometrical shadow region. Uh, if we see a vertical tube light through a parallel narrow slit made between two fringes capped in front of eyes, alternate light, bright and dark fringes are seen. Both these events can be explained on the basis of diffraction of waves. Another example of diffraction of waves is the reception of radio signals by different receivers. Thus, the event of bending of waves around the corners of an obstacle, that is diffraction, is general property of the wave. The phenomena can be observed very clearly in the sound waves and radio waves, but rarely observed in the light waves. In special cases, when the obstacle is very small, this event can also be observed in the light. The phenomenon bending of light waves around the obstacle and entering into the region of the geometrical shadow of the obstacle is called diffraction of light. So, diffraction of light is observed only at the boundary of the geometrical shadow. In short, the phenomena of a deviation of light from its rectilinear propagation is called diffraction. The diffraction phenomena was first discovered by Grimaldi in 1665, but correct explanation of this phenomena was given by Fresnel in 1818 on the basis of Huygens wave theory. So, dependence of the diffraction of waves on the size of the obstacle and wavelength of the waves on the following parameters: size of the obstacle, wavelength of the waves. So, now I would like to some light on the difference between the interference and the diffraction. Interference is due to the superposition of waves, that is, two or more but finite in numbers emitted from the monochromatic coherent sources. And the diffraction is due to the superposition of secondary wavelets emitted from different points, infinite numbers of the same wavefront. In an interference pattern, the minima are usually almost perfectly dark. In the diffraction pattern, the minima are not usually dark. In an interference pattern, all the bright fringes are usually of same intensity. And in the diffraction pattern, the intensity of bright fringes decreases as the order of fringe increases. The interference fringes may or may not be equally spaced. The diffraction fringes are never equally spaced. In general, the number of observed interference fringes is quite large, and in diffraction, the number of observed diffraction fringes is quite small. And the diffraction are of two types: Fresnel and Fraunhofer diffractions. Fresnel and Fraunhofer diffraction. So there is a difference between the Fresnel and Fraunhofer diffraction. I would like to just give a small introduction between the difference between the Fraunhofer and Fresnel diffraction. In Fresnel diffraction, the source of light or observation point are both at finite distance from the diffractor, whereas in Fraunhofer diffraction, the source of light and observations point both are effectively at infinite distance from the diffractor. The incident and diffracted wavefronts are either spherical or cylindrical. The incident and diffracted wavefronts are plane in Fraunhofer diffraction. In Fresnel diffraction, no lens or mirror is used. Whereas in Fraunhofer diffraction, diffracted light is collected by lens. In Fresnel diffraction, distance are important in this class of diffraction, whereas in Fraunhofer diffraction, angular inclinations are important in the case class of diffraction. In Fresnel diffraction, the diffraction pattern is shadow of the diffracting element modified by the diffraction effects. In Fraunhofer diffraction, the diffraction pattern is an image of the source modified by the diffraction at the diffracting element. In Fresnel diffraction, the center of the diffraction patterns may be bright and dark depending upon the number of Fresnel's half-period zones. Whereas in Fraunhofer diffraction, the center of the diffraction pattern is always bright for all rays parallel to the axis of the lens. So, next. So, diffraction by a single slit or disk. The resulting pattern of light and dark strips is called diffraction pattern. This pattern arises because different points along a slit create wavelets that interfere with each other just as a double slit would. Next. The minima of the single slit diffraction occur when d sine theta equals to m lambda, where m is equals to plus minus 1, 2, 3, and so on. Diffraction grating. Uh, Diffraction grating consists of large number of equally spaced narrow slits or lines. A transmission grating has slits, while a reflection grating has lines that reflect light. The more lines or slits there are, uh, the narrower the maximum of the diffraction pattern are defined by sin theta equals to m lambda by d, and these are the fringes obtained. The spectrometry and spectroscopy. A spectrometer makes accurate measurement of wavelength using diffraction grating or prism. So, next, the spectrometer makes an accurate measurement of the wavelengths using a diffraction grating or prism. The spectrometry and spectrometer and spectroscopy. The wavelength can be determined to high accuracy by measuring the angle at which the light is diffracted. The wavelength is given as d by m sin theta. Atoms and molecules can be identified when they are in the thin gas through their characteristic emission lines. Interference in thin films. Another way, path lengths can differ, and waves uh, interfere is if the travel through the different media. If there is a very thin film of material, a few wavelength thick light will reflect from both the bottom, top of the layer, causing interference. This can be seen in the soap bubbles and oil slicks, for example. Interference in thin films, the wavelength of light will be different in the oil and in the other, and the reflection at point A and B may or may not involve the reflection. Interference in thin films we had already discussed. Similar effect takes place when a shallowly curved piece of glass is placed the above concentrated appears. We can also create a thin films of air by creating a wedge-shaped gap between two pieces of glass. Now, interference in thin films. These are the problem-solving interference. Interference occurs when two or more waves. These are some summary points. Now, the Michelson interferometer. The Michelson interferometer is centered around a beam splitter, which transmits about half the light hitting it and reflect the rest. It can be very sensitive measure of length. Now, this is all for this lecture. Thank you. Thank you all.